Hey everybody, welcome back to another edition in geometry. It's Mr. Anderson here with you. Today we're in section 8.2. We're going to talk about probably one of the most famous theorems or formulas or equations there is, the Pythagorean theorem, okay, and the formula that goes along with that. All right, so today we're going to use the Pythagorean theorem, and number two, we're going to use the converse of the Pythagorean theorem, okay? All right, so let's take a look at the Pythagorean theorem to see what it says, and you probably already have this memorized even, which would be great. But if you notice here, it says in words, it's got to be a right triangle. See, the key thing here, one of the key things, ooh, that's not a very good underline, but one of the key things about Pythagorean theorem is it has to be a right triangle. Okay, this doesn't work in all triangles, just right triangles. So that's the first thing. The second thing is it says the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. Well, you know this formula here, a squared plus b squared equals c squared. What people get confused on is which one is c, okay? So notice how here's c. C is the side that's across from the 90-degree angle. This is the hypotenuse, okay? This is the hypotenuse. C is the hypotenuse. C is always the one that's away from or across from the 90 degrees. The A and the B are always the two legs. Okay, this is a leg, this is a leg. So A and B are always the legs. C is always the hypotenuse when you do the Pythagorean theorem. So make sure you get that in the right order. Okay. Now, this looks really complicated. I just kind of threw this in here. To me, this is really neat, okay, because maybe I'm a math nerd or whatever, but a cool math nerd, of course. This goes through, remember what we were just doing here in the last section with a right triangle, you can do an altitude. Remember all those proportions that we'd set up in the last video? This just goes through showing how you can take those proportions that we did in the last one and come out with the Pythagorean theorem, so it's pretty neat. You just see that, like, for example, c over a equals a over y, c over b equals b over x. We did some of that last time. And the fact that a times a is really a squared and b squared. And if you go a squared plus b squared equals the cy plus the cx, and then you factor out a c and y plus x. If you notice here, y plus x is really c. Well, that's a c squared. So don't worry about that. I just want to put it in there to make myself feel better about this. Is really cool. If you're interested, you can pause the tape and look through all that stuff and check it out. But let's move on. All right, first example then. Okay, we're just going to do the Pythagorean theorem here. So remember, it's just a squared plus b squared equals c squared. All right, so remember, we just have to get this in the right order. So if you look at this, here's the 90-degree angle. The two sides that make up the legs are 4 and 7. So this is a leg, and this is a leg. That means this is the hypotenuse. Okay, so 4 and 7 are our A and B. Does it matter which one's A and which one's B? Nope. Just use one for one and one for the other. Doesn't matter. So this is going to be 4 squared plus 7 squared equals c squared. All right, 4 squared is 16. 7 squared is 49. And then we've got, what, 16 plus 49 gives us 65. That's c squared. Okay, how do we undo squaring something? What undoes squaring something is taking the square root. So we take the square root. As long as we do it to both sides, we're cool. And so this means this is just going to work out to be c, and this is the square root of 65. Now, we would probably like to see if there's some way that we could simplify that. I think in this case, if I remember correctly, this is going to do it because it's at least simplifying y. This would simplify down to 5 and 13. Remember how we simplified before? There are no dates here. 13 and 5, nothing is left out of those. So we could just leave that as square root of 65. Occasionally, they might ask you to put that in decimal form, and then you can just plug that into your calculator and give the decimal form of that. Okay, let's look at another one. Okay, how about this one now? Well, okay, I didn't even touch it. This is the 90-degree angle right here. So 8 is a leg, and x is a leg. And this is the hypotenuse out here. Okay, so that means we're going to use x and 8 are going to be the a and the b. So we're going to go x squared plus 8 squared equals 12 squared this time. Notice our variable is in a different place. Let's just simplify everything and get x by itself. So I have x squared plus 64 equals 144. Okay, so I've just multiplied those out. And so now I'm just going to subtract 64. So I have x squared equals 80. And then what undoes squaring something? Taking the square root. And so that means x is going to equal the square root of 80. Now in this one, could we simplify this a little bit? I think we might be able to. And so if you think about this, okay, let's say we could do here 8 and 10. Square root of 8 could be 4 and 2. 10 could be what? 2 and 5. And you go, well, first of all, here's square root of 4. That by itself is going to be 2. Here's a date, 2 and 2. So that's going to be another 2. And then the square root of 5 just has to stay as it is. That's square root of 5. So all together here, when we put this all together, 2 times 2 is 4. So we can say x is going to equal 4 square root of 5. That will be our final answer. Okay? All right, moving on. All right, a Pythagorean triple. All right, now this is kind of interesting. You go, well, what's a Pythagorean triple? Is it where the Pythagorean hits a triple, hits one into the right field gap and gets all the way to third base? No, no, it's not baseball. A Pythagorean triple is just a set of 3 non-zero whole numbers that make a squared plus b squared equals c squared work. Okay, so it's just 3 numbers that you can plug into this formula to make it work. There's a whole bunch of them, and I'm going to put up a list here, and we'll talk about a couple of things. These are some of the common ones, I guess you could say. I would highly recommend this one right here, 3, 4, 5. Memorize that one. That one is really common. You know, that's one that you should just have memorized, 3, 4, 5, 3, 4, 5. Because if you plug that in, the 3 goes in for A, the 4 goes in for B, the 5 goes in for C, you would notice it works out. Also, notice below this here, all of these are just multiples of those numbers. So on this next level, you just multiplied 3 times 2 to get 6, 4 times 2 to get 8, 5 times 2 to get 10. So any multiples of 3, 4, 5 would also work. Okay, so that's what this means down here, 3x, 4x, 5x. No matter what number you put in for x, that will work. This is also probably pretty good. Maybe secondarily, this is kind of a good one to memorize. 5, 12, 13 also is one that works. And again, notice these are all numbers down here that are multiples of 5, 12, and 13. As you start getting up and see some of these other ones, it gets hard to remember those. But if you could at least remember 3, 4, 5, and 5, 12, 13, that will probably help you, maybe even on the ACT. Okay, so let's look at a couple of things here, a couple of examples. Now, could I take this example and just do the Pythagorean theorem to solve this? You know, a squared plus b squared equals c squared. I sure could. But, you know, what we're trying to do here is use a Pythagorean triple to solve this. So again, if you can kind of remember some of those Pythagorean triples, you might be able to take a shortcut here. And if you go, look at the 26 and the 24, and you think, hey, you know, they're both even. I could divide them by 2, right? So, you know, I've got the 24 and the 26. If I divide them by 2, let's say I divide this by 2. 24 divided by 2 is 12. 26 divided by 2 is 13. So think about the other side that's missing. You go, hey, do you remember anything that from that list of Pythagorean triples? Something 12 and 13? Oh, if you remember, that would be 5. 12 and 13 would make that work. But now remember, 5 is not the answer here because our numbers are all doubled from this, right? 5, 12, and 13. So what goes with the 24 and the 26? This would be 10. You'd have to double it. So 10, 24, and 26. So in this case, we could say x would equal 10. We wouldn't have to work out the whole formula. I could just simplify that a little bit, okay? How about another one? All right, we'll look at this. All right, look at the 2 numbers that we have. could they both be divided by something, the same thing? Well, let's think about it. We got 36 and 39. They could both be divided by 3, right? So this time we could divide them both by 3. So if you divide 36 divided by 3, it's 12. 39 divided by 3 is 13. Hey, look at this. It's the same thing. This would be 5, 12, and 13. But this time, since we had to go times 3 from our kind of our base Pythagorean triple here, this would be what? 15 this time. Okay, so here we would say x would have to be 15. So if you can kind of think along that lines, you don't have to go through all the work of doing the a squared plus b squared. You can save yourself a little time. All right, here's an example. Use a Pythagorean theorem, kind of a real world situation. Somebody is leaning their ladder up against a wall. We want to see how far away from the wall it is. Well, I could just go through that whole process again. Remember, here's the 90 degrees. So the legs are going to be the x and the 16. So I'm going to do x squared plus 16 squared equals 20 squared. And we're going to work that out then, okay? So x squared plus 16 squared is 256 equals 20 squared, which is 400 minus 256. 144, so x squared equals 144. Take the square root of both sides. X is 12, so 12 feet. Hey, all right, cool. You know what you also could have done? Pythagorean triple. We could have done the same thing that we just did on the previous ones. Look at 20 and 16. What could they both divide by? 20 and 16 divide by 4. So 20 divided by 4 is 5 and 4. And if you think about the Pythagorean triples, what something 4 and 5 would be what? I've got it backwards here. But 3, 4, and 5? Like, oh, 3, 4, and 5. That's a Pythagorean triple. But remember then, just to work this backwards, since I had to divide everything by 4, I just go 3 times 4, which would give me 12. And you notice, hey, that's what I got right here. So either way, I just wanted to show you can work this out all the way as a regular Pythagorean theorem problem. Or in this case, you could have figured this out as a Pythagorean triple. Okay. All right, the converse of the Pythagorean theorem. All right, all this is saying here, and we're going to use this in a certain way here, is remember, if we have a right triangle, you can do a squared plus b squared equals c squared. So here they're saying if you have a situation and the number for a, if you square it, plus the number for b squared, if that equals c, then you know you have a right triangle. So you may not know you have 90 degrees, but if this works out, a squared plus b squared equals c squared, you know you've got a right triangle. Okay, well, what that leads us to is this as well, are these Pythagorean inequality theorems saying that, and we'll see how this works in a second here, if you have c squared, now it's written backwards from what we're used to, but c squared's first here, and I think that's probably a good way to think about these. If c squared is less than a squared plus b squared, then ABC is acute. So think about this. Look at this drawing over here. If you started with, we've got a right triangle of some sort here. We know that a squared plus b squared equals c squared. We know that this is a right triangle if these equal. Well, now if c squared starts getting less, what this length of this side here is going to get shorter. And what happens is it pulls in, and this side gets shorter, and then you get less than a 90-degree angle, which makes these all less than 90, which makes it acute. Likewise over here, if c squared is greater than a squared plus b squared. So again, you start with this, but if c squared is going to start getting bigger, this side is going to get longer, and so it's going to get looking like this, which means it's going to split this angle out further than 90, which makes you have an obtuse, well, same thing, an obtuse angle. And then it gives you an obtuse angle here, okay? So let's look at a few examples with that. First of all, we want to determine is 9, 12, and 15, number one, can they be measures of a triangle? And if so, then is it acute, right, or obtuse? So remember from a while back, to figure out if something can even be a triangle, remember any two sides have to add up to be longer than the third side. So we got to check that first. So is 9 plus 12, is that greater than 15? Yep, 9 plus 12 is what, 21? So, yep, that's good. Is 12 plus 15, is that greater than 9? Yes, of course. Both of them by themselves are. And then finally, is 15 plus 9, is that greater than 12? And again, the answer is yes. So this can be a triangle. So now what we have to do is just figure out which one of these it is. So how do I know which one is A, B, and C? If you're doing this, working this out this way, A and B are always going to be the two smaller angles. The two smaller numbers. The C will always be the biggest number. So in this case, 15 is going to be C, 9 and 12 will be A and B. So we're going to just do this. Is 9 squared plus 12 squared. What does it do? Does it equal or is it greater than or whatever? 15 squared. We're just going to compare those two and see what we get. So 9 squared is 81. You probably got that. 12 squared is 144. And 15 squared is 225. So let's see. Do they equal each other? Well, 144 plus 81 is 225. And so guess what? They equal each other. So we would say this is a right triangle because the two sides equal each other. All right, how about this one? Again, we got to make sure this can be a triangle. So is 10 plus 11, is that greater than 13? 21, yep. What about 11 plus 13, is that greater than 10? Yep. And finally, is 13 plus 10 greater than 11? Yep. Okay, so this can be a triangle. So let's go through it again. A and B are the two small numbers. 10 squared plus 11 squared. Does that equal 13 squared? So 10 squared is 100. 11 squared is 121. 13 squared is 169. Yep. And so when you add this together, 100 and 121 is what? 221 and 169. So what do we have? And actually, okay, that's okay. I probably should have written this with the C first to make it a little easier. I think when I write it the normal way, it gets confusing here. But let's think about this. So remember, the C was on the right here. Is the C bigger or less than the A and the B squared? Well, the C side is less than, right? So if the C side is less than, that means this is acute. That's why I said the way they did that on the previous slide, they wrote the C first. I think that's easier because that's what you're kind of basing it on, is C greater than or less than. So here the C is coming second, but it's less than the A and the B part. So this would be acute. All right, what about this one? First of all, 7 plus 8, is that greater than 14? Yep, 15, good. 8 plus 14, is that greater than 7? Yes. And then finally, is 14 plus 7, is that greater than 8? Again, yes. That's fine. Okay, so we're good. Let's do it again. This time I'm going to try to do it where the C comes first, maybe. I don't know, maybe that'll be weirder, but let's see what happens. So the C is 14, so if we do 14 squared, does that equal 7 squared plus 8 squared? All right, well, what's 14 squared? 196. 7 squared is 49. 8 squared is 64. So 64 plus 49 is 113. So in this case, the 196 is bigger. And again, remember, I wrote this where the C comes first this time. So this is the C. This time C is bigger than the A squared and the B squared. So this time it would be obtuse or obese. Okay? One more. How about this one? Again, let's check it. if I do 14 plus 18, does that equal 33? Or is that bigger than 33? Sorry. And if you add these together, oh, wait a minute. This is 32. Is 32 bigger than 33? No, it is not. So here's a situation where this does not even make a triangle. And so this is not even a triangle. And so since it's not a triangle, we can't figure out if it's obtuse or acute or right. So yeah, so you do want to check these to make sure that this will make a triangle. That is it for today. So a little bit today about the Pythagorean theorem and its converse. Appreciate you guys being here, and we'll see you next time when we talk about something else geometry related. I can't even remember what it is now. See you later. Bye.